All right, so today I'll be talking about some algorithmic game theory topics, primarily focused on the notion of like fair division. So the problem that we'll be thinking about is we have, say, I'm trying to figure out which I want to use n for and which I want to use m for. We'll say we have m goods and n agents. And we want to fairly divide these goods up between all the agents. So the question is like, what does it mean to fairly divide goods between agents? And if our goods are things that we can cut in half, this is really easy, right? Imagine we have some birthday cake. Now, if I want to divide this birthday cake up between everyone in this room in a fair way, it's very easy. I just cut this cake into like 10 slices. We each get a slice. All our slices are the same size. We're all very happy. We consider this fair. But this problem becomes a little bit more difficult when what happens if you have an iPhone? How you can't cut an iPhone in half. That would not necessarily end very well. I don't think anyone would be happy with 1/2 or 1/10 of an iPhone. So we need some kind of other notion of fairness when we're thinking about dividing indivisible goods. So for dividing goods that are divisible, like birthday cake, bread, whatever, a notion that we like to think about is what we call envy-freeness. And the idea behind envy-freeness is that for all agents, for all I values their bundle at least as much as they value any other agent's bundle. So in essence, we say each agent has some valuation function that says how much they value a good or part of a good. And then we say that I envy another agent if I think their bundle is worth more than mine. So if we were to cut this cake where Anakin gets 2/3 of the cake and I get 1/3 of the cake, then I would probably envy Anakin because I would value 2/3 of the cake more than I would value 1/3 of the cake. Now, you can show that if you have divisible goods, envy-free allocations always exist because you can just kind of chop things up, right? Now, the question is, what about when you have indivisible goods? Well, it's very easy to see that envy-free allocations don't necessarily exist if your goods are indivisible. So as an example, let's consider one iPhone and two people. And both people value the iPhone at $1,000. Now, if I were to allocate this iPhone, it's going to have to go to one of these two people. The person who doesn't get the iPhone is going to be envious. So we know envy-free allocations don't necessarily exist when we have goods that are indivisible. So we want to get kind of the next best thing. We want to try and get some kind of fair enough allocation. So one initial idea of how we could do this is we'll define what we call envy-free up to one good, or EF1. And the definition of an EF1 allocation is that for all agents I, an agent values their bundle more than the other agent's bundle minus any good that we choose. So what this means is, let's imagine we'll imagine both of our agents have the same valuation function. They both think the items are worth the same amount. And we have agent 2. So let's say I give 3 things here worth 1, 1, and 2. So the value is 4, and agent 2 gets 2 things, each worth 1. So it has a value of 2. Now, I claim that this is an EF1 allocation. The reason that this is an EF1 allocation is agent 1 thinks they got $4 worth of stuff, and that agent 2 got $2 worth of stuff. So agent 1 would not envy agent 2. But if I look at agent 2, okay, agent 2 does envy agent 1, right? Agent 2 got $2 of stuff, and agent 1 got $4 of stuff. But if I remove the good agent 1 got that is valued at 2, then agent 2 got $2 worth of stuff, and agent 1 got $2 worth of stuff. So 2 does not envy 1 after removing the good valued at $2. Now, this would not be an EF1 allocation if I add another good worth $1, because now that would give us a value of $5 for agent 1's bundle. And even if we remove the most expensive good, the good worth $2, agent 1 will have a bundle worth $3, which is more than agent 2's bundle. So in this case, we're kind of like just on the edge of being EF1, but if I give agent 1 anything else, we'll lose that EF1 property. Does this make sense to everybody? So a natural question for us to ask is whether or not EF1 allocations always exist. Because seems like it might be a reasonable definition of fairness, right? So first thing we'll do is we will restrict ourselves to what we call additive valuations, because when you get into valuations that are not additive, funky things happen. For example, suppose your goods are like chemicals, and if 2 bad chemicals mix, they form poison and you die. You have this weird valuation function that says, if I get more stuff, my value for that bundle might go to 0 because it would kill me. So that's very hard to reason about when we're thinking about allocations. And a lot of real world settings are maybe cases where you want to think about giving more goods to someone should give them more value. And there's a few ways you can capture that. And the easiest one for us to think about is going to be additive. So we'll say that an agent's bundle, then agent's value for some bundle is equal to simply the sum of the values of each good in that bundle. So for example, let's say an agent values good 1 at $10, good 2 at $5, and good 3 at $1. The value of the bundle containing good 1 and good 3 would be 10 plus 1 equals $11. So the notion that we'll use to try and start doing EF1 allocations is we'll create something that we call the envy graph. And in the envy graph, our idea is pretty simple. We're going to say that we add a vertex for each agent. And we have an edge from I to j if I envies j. So for example, if we have the case above where I had 1, 1, 2, 1 on agent 1, and agent 2 has 1 and 1, our graph would look like I have agent 1, I have agent 2, and I have an edge going from 2 to 1 because agent 2 on the right envies agent 1 on the left. Note that this is just for envy, we're not saying EF1. So these edges, I could add in a bunch more things into agent 1 and our graph wouldn't change. There is just only ever an edge when there is envy. Make sense so far? All right, so now I want to make a claim, which is that we can assume without loss of generality that the envy graph is acyclic, which is perhaps not a super obvious claim, but let's think about what does a cycle in the envy graph mean? Let's imagine I have some sequence of agents that looks like this. I have a cycle between these 4 agents. What this tells me is I'm going to number these agents 1, 2, 3, and 4. Agent 1 would like the bundle of agent 2. Agent 2 would like the bundle of agent 3. Agent 3 would like the bundle of agent 4. And agent 4 would like the bundle of agent 1. So what can I do here? Well, I can give the bundle of agent 1 to agent 4. I can give the bundle of agent 4 to agent 3. I can give the bundle of agent 3 to agent 2. And I can give the bundle of agent 2 to agent 1. So by rotating these bundles, all of these edges involved in this cycle would disappear. Yes.
But what if like 4 also envied 2's bundle and 3 also envied 1's bundle and et cetera, et cetera? Can they still envy each other even after rotating?
Yes, so we do need more to this proof still. So yeah, it'll be helpful to build intuition to draw out what would happen in that case. So let's imagine I have 1 to 2, 2 to 3, 3 to 4, like this. And you said what happens if 2 envies 1 also?
If because after you rotate, 1 gets 2's bundle, so what if 4 originally envied 2 as well?
All right, so 4 envied 2.
And then similarly, 3 and I want to draw this bigger. 3 envies 1, 1. 3 envies 1. Is 2 envies 4 and then 1 envies 3.
All right, so
after a rotation, they all envy each other still.
There is still some envy here, right? So one observation we can make is after we eliminate a cycle, so after a rotation, every agent will, if agent 1 envies agent 3, the amount that agent 1 envies agent 3 will only decrease, right? So because agent 1 got a bundle that they think is more worth it, right? And now we observe that, sure, so if I do this rotation, what I'm going to end up with is a case where I should draw this a little further down. We have 1, 4, 3, and 2. So agent 1 previously envied agent 3, and now they got a bundle that they envied, right? So they're happier. So it is possible that 1 might still envy agent 4 now, because they previously envied agent 3, or sorry, the bundles are going backwards. So now 1 might possibly still envy agent 2. So I would have an edge from 1 to 2 still, perhaps, or that envy might go away if we're lucky. Now, likewise, agent 3 envied agent 1. So if we look at where agent 1's bundle is going to, that's going to 4. So there might still be an edge from 3 to 4. And 4 envied 2. So if we look at where is 2's bundle going, it's going to 1. So 4 could still envy 1. And if I look at 2, 4's bundle goes to 3. So I might end up in a situation like this. I can rotate again. So after enough rotations, because every rotation is going to delete at least one edge from that is part of this cycle, you will eventually end up in a scenario where you have no more cycles. So since greater than at least one edge involved in our cycle is deleted, after enough rotations, this graph will be a DAG. Now, I won't go through the algorithm to do this, partly because I don't entirely remember it, but you can actually do this elimination in polynomial time if you construct things properly. So now we want to use this idea of the envy graph to assign goods and generate an EF1 allocation. So let's think about if there is an agent. So given some envy graph, we know that a sink in the envy graph does not envy anybody. Right, because a sink has no outgoing edges, an outgoing edge represents envy, so a sink does not envy anybody. And likewise, a source is not envied by anybody because there are no incoming edges to a source. Now, I claim that giving a good to a source will only ever make someone envy the source up to EF1. So imagine we have some envy graph. Our claim is that if I give a good to source, this will cause at most EF1 envy from other agents. And the proof of this is easy to see because the definition of EF1 is that I can remove any good I want from the bundle of the source. So I can simply remove the good that was added and the envy goes away. That's the definition I need for EF1. So my proof is that I can remove the added good and envy goes away. And that is the definition of EF1. And this is all we need to get a very simple algorithm that shows EF1 allocations always exist. The algorithm is, while there exist unallocated goods, we give a good to a source, and then eliminate cycles. Because we eliminate cycles after every step, we're guaranteed that there's always a source. We're giving one good away every round. So after one round for each good, we've allocated all of the goods. And because we are only ever giving goods to a source, the envy will only be up to EF1. And we can observe that eliminating cycles also preserves the fact that the envy on edges is up to EF1 only, because after you do a rotation, agents only become happier. So if agents get happier, the envy would stay EF1. Does this make sense to everybody? All right, so EF1 always exists. Now, EF1 is maybe kind of a weak notion of envy, because I could give some kind of insane thing, like I give agent 1 something worth 10 to the $10, and agent 2 something worth $5, and something like this. Now, this is an EF1 allocation because I can remove the good valued at 10 to the 10, and now both agents have a bundle valued at $5. So that's kind of but this is a very unfair, unbalanced allocation, right? So we want some kind of stronger notion of envy freeness, but that still allows us to remove goods, because we know that if we don't allow the power to remove goods, the allocations might not always be possible. For example, when you have one good that 2 people want, only one person can get it. So we'll define envy freeness up to any item. And the way we define envy free up to any item is that for all agents I, the value of I's bundle must be at least the value of another agent J's bundle minus G for all goods in XJ. This is equivalent to saying that agent I must no longer envy J after removing their least favorite good from J's bundle. Does this definition make sense to everyone? Now, we had a very straightforward algorithm that shows EF1 allocations always exist. That is not the case for EFX allocations, which are envy free up to any item. It is actually not known whether EFX allocations exist beyond 4 agents. So we know they exist when you have 3 agents. We don't know the case of 4 agents or higher. We know it for some restricted settings, which I will go over, but we don't know it for the general case of 4 agents with just arbitrary additive valuations. We know some approximations, but we don't have any exact guarantees. So one case where we do know about if EFX exists is the case of identically ordered valuations, which means agents can value items differently from one another, but if you sort the items by value, that sort would be the same across every agent. So that means that value of good 1 for agent I is less than or equal to value of good 2 for agent I, and so on, up to value of IN for all IM for all agents I. So they all think good 1 is the worst good 2 is the second to worst good, and good M is just the best good that you could possibly have. So when we have identically ordered valuations, we can actually use the similar technique to what we did for EF1. Because the trick that we can do is EF1, we just said, we're going to assign goods in whatever order we want. And that's fine because we care about only removing one good. But in the case of identically ordered valuations, there's a slight tweak we have to make, which is we want to figure out some order to assign the goods such that if we assign the goods in that order, the NV will be up to EFX only. So let's think about what that order should be. So our intuition is we still need to assign goods to sources. It never makes sense to assign a good to a sink because that would only increase the amount someone envies the sink. So we want to assign goods to sources still because sources are not envied by anybody. Now, if we're assigning goods to sources, there's a case where we can run into, which is, let's imagine I have two agents, agent one and agent two, and agent one envies agent two. We know we want to assign a good to agent one because they are not envied by anyone, but they do envy agent two. We want to make them happier. So let's imagine that I have something like agent two has something worth $100, and over here I've got something worth $90, and let's say $94 and something worth $5. And let me do some mental math here. I think I'll need something worth like 2 here, and that gets me 99. So it's 102, 99, 99 plus 4 is 103. We want these to be essentially very close in value, so we're going to say that this guy has something worth 100 and something worth 2 as well.
So neither envy each other.
Or sorry, let me make that 2 minus epsilon. Now, if I assign some good to agent 1, say with value 2 epsilon, or some very small good, what could happen? I don't think I did the math right for it to work out in this situation, but if I assign a very cheap good to agent 1, the issue I'm going to run into is that according to my definition of EFX, I need to remove the worst good from this bundle. Now, if that worst good becomes really, really cheap, then let's say neither envy each other, actually. So I've got 100, 2, and maybe in this case, it's 100, 102. And this doesn't work when your evaluations are identical, by the way. If your evaluations are identical, this doesn't work. So we'll need to draw this out as a table, actually. Let's imagine good 1, good 2, and good 3, and my V1 and V2. So they both value good 1 the least. This one, agent 1 values it at epsilon. Agent 2 values it at 2. And then I have good 2 is valued at 4. This is valued at maybe 2 because this is not strict equality. And then this is valued, say, at 5. And I'll figure out what I want that V2 to be. So if I give agent 1 some goods 1 and good 2, and then agent 2 gets good 3. So Agent 2 thinks good 3 is worth 5, let's say. So they're going to see themselves as being happier than Agent 1, right? They got the good that's valued at 5, but they think Agent 1 has a bundle worth 4. And Agent 2 is going to be happy. They think they have a bundle worth 4 plus epsilon, but Agent 2 has a bundle only worth 4. So but neither agent envies one another here. But there's an issue that happens, which is, let's say I assign a good of value 1.5. So let's imagine a new good somewhere in here. So perhaps this 2 becomes a 1. And then I throw in some good with value like 3. Now what happens is, because I have this epsilon is the worst good. So when I assign good 3 to agent 1, now, oh, sorry, let me name this.
And both agents agree that it's a value of 3?
Yes, the value of 3. And this is good like 1.5. I'm inserting in between good 1 and good 2, right? You can, I'm not going to renumber everything, but you get this good 1.5. Now, value agent 1 is happy. They think they have epsilon plus 3 plus 4. But if we look at agent 2, v2 of x1, it's going to look like epsilon plus 3 plus 4. But if I look at v2 of x2, then their bundle is worth, say, I'm going to make this 7 minus epsilon. All right. So now if I remove the cheapest good from x1, I get 7, which is greater than 7 minus epsilon. So this breaks our EFX because I assigned a cheaper good later on. So based on this, our intuition is that we want to start assigning the cheap goods first and move on to assigning the more expensive goods later. Because if you add a more expensive good later on, the minimum will never change. And the key property here is that all agents see the worst good in another agent's bundle in the exact same way. We all collectively agree on some ordering of the items. So we're all going to have a shared opinion on what the worst good is. So if that never changes later on, then we can maintain EFX. So our algorithm is going to be for goods 1 up through n. Remember, we said 1 is everyone's least favorite good, n is everyone's favorite good. We will assign GI to some source, and then we'll rotate bundles. And we know that since we're assigning GI to an agent who isn't envied by anybody, and GI is going to never be the minimum, we're going to preserve EFX. And and rotation only improves everyone's like perception of how much their bundle is worth. You only get happier when you get a bundle that you previously envied. So this maintains EFX. Actually, let me think. Should this be 1 up through n or n down to 1?
Cheaper items first, right? So
Yes. 1 up to n. No, sorry, it's n down to 1. So the reason it's n down to 1 is because a source is not envied by anybody. So if you give a source something that is worth too much, then people might envy them a whole lot, but the minimum is really, really small. And if the minimum is really, really small, you can't remove it. So instead, if you assign the bigger items first, you are going to, we can observe that if we consider arbitrary agents I and j, so we'll suppose that I is our source. So we know that Vj of xj is greater than or equal to Vi xi previously. And now I'm adding one new good to xi, right? That one new good I'm adding is going to be the cheapest good in xi. So this implies that if I just remove the cheapest good, then I get the same equality I had before, because that's xi union with the new good, but then I take out the new good. So this is still EFX. So we want to go n down to 1. For the reason that, as we showed above, if we assigning cheap goods can screw us up later on. Now, this also admits another case where we know EFX exists, which is identical valuations. Because if you have identical valuations, you have the same order. And we just showed that the same order exists. Now, I'll wrap up in the last few minutes with some work on like how we can look at approximating EFX, because finding exact EFX seems to be hard. It's conjectured to exist, at least for the n equals 4 case. It has been shown that EFX exists when you have 4 agents and 3 distinct valuation functions. So 2 agents have identical valuations and the other agents have whatever. So we're very, very close to getting it for n equals 4. Nothing on n equals 5, which is a bit unfortunate. You can also show that it exists for n agents if you are willing to have n minus 1 goods unallocated. There's also some connections to graph theory, and where if you can prove a bound on what's known as the rainbow cycle number, an improvement on that bound translates into an improvement on the bound on the number of unallocated goods while maintaining EFX. And now I'll talk briefly a bit about some of the work I've done through CS580 on approximating this, which is there's a very simple algorithm we can think about, which is, let's imagine we have exactly, so we'll say m is equal to k times n. So we have the number of goods is some multiple of the number of agents, just to make our analysis easier. And we'll go in m over n rounds. And in each round, we will topologically sort our NV graph. And then after we topologically sort our NV graph, we will allow each agent to pick their favorite good. And once agents have picked their favorite good, we will eliminate cycles. And this enforces a constraint that every agent gets the exact same numbers of goods, right? Which necessarily guarantees that this will not always generate an EFX allocation, but this actually gets a pretty decent approximation. So we'll define D is the maximum difference between valuations of consecutive items for a given agent. or di. So what this is saying is that let's imagine I value good one at $1 and good two at $5. D would be equal to 4. That's the largest gap between values of any two like consecutive goods in the sort. And sigma I is simply the minimum. And then we define a global D to be the maximum of all D, and a global sigma to be the minimum of all of these sigmas. So this, and then we'll define rho to be sigma over D. So essentially rho is a measure of how evenly spaced out your valuation functions are. So if you have if you're just ranking items, like item one is worth 1, item 2 is worth 2, and so on, like a preference list, rho is equal to 1 because the minimum gap is 1 and the maximum gap is 1 between any two consecutive items. And an observation you can make with this above algorithm is that after every round, the difference between two agents' values, so vjxi minus vjxj, is bounded above by d times n. This is because in the worst case, agent I picks first, agent j picks last, and the difference between consecutive items is bounded by d. So you have n agents, they each pick something worth d, then minus d, minus 2d, minus 3d. So the worst case NV after a given round is d times n. And there's some kind of annoying algebra, and you can show that this gives a 1 minus 4n squared over rho m squared EFX approximation. And this is essentially saying that once your number of goods gets big enough, you'll get arbitrarily close to having something that is EFX. And for reference, the best known approximation in literature is a 0.618. So this essentially says you don't need that many goods to beat a 0.618 approximation if your valuation functions are well spaced. If rho is small, you're kind of cooked. You need a whole lot more goods. Yeah, that's all I have. Any questions? Yep.
So next week is like the next set of these short and sweet meetings that we did, things like 2 or 3 weeks ago. So it'll be 3 separate people presenting, doing short talks of around 15 minutes each. So you get a cool variety of things. And then the meeting after that, Professor Jeff Erickson will be presenting on some stuff related to Conway's Game of Life. So that'll be pretty cool. And then we're done. Semester's over. So otherwise, that's about it. As usual, there's stickers in that box if people don't have stickers and or if they want more stickers. Otherwise, yeah, see you all next week.